Hi everyone. Today I wanted to talk to you about the unit circle. A lot of people tell me that the unit circle is very hard for them to understand and they think that it's just beyond their comprehension. But that's not true. The unit circle is actually really simple if you break it down into pieces. Because this is kind of a long-winded concept, we're going to do it in two parts. So for today, we're actually just going to set up the special right triangles that we use in building the unit circle. And then next time, we'll put them all together and make the circle out of it. So here we go. Okay, so the first special right triangle we're going to look at is the 45, 45, 90 triangle. And this triangle is special because it has two angles that are the same. It's actually an isosceles right triangle. So it has a 45 here, a 45 here, and when I say 45, I mean 45-degree angle. And the right angle is here. Now when we're talking about the unit circle, we're really only interested in angle A, because that angle right here, A, 45 degrees, is going to be the one that's going to be at the center of our circle once we set it up. But when we have a 45, 45, 90 triangle, we have a special relationship that is built up among all the sides. So our two legs of our right triangle are the same because they are opposite the angles that are congruent to each other, right? This one is opposite there, this one is opposite there, and these two are congruent. So we're going to call them both x. And what we have here, the hypotenuse, ends up being x radical 2. Now we can quickly come to that conclusion using the Pythagorean theorem if we say we have these two legs, so the first leg squared plus the second leg squared is going to equal the hypotenuse squared, right? I'm calling this C. So I have 2x squared equals C squared. I take the square root of both sides. And we end up with x radical 2 equals C. And that's how we get this hypotenuse. So whenever we have a triangle that's shaped like this, we're going to have two sides that are congruent. We call them both x, and the hypotenuse is going to be x radical 2. So now, in order to apply this to the unit circle, we need to just do a little bit of algebra. The idea behind the unit circle is that the hypotenuse of any triangle we put into it is going to equal 1, because the hypotenuse is going to become the radius of the circle, and the unit circle is a circle whose radius is 1. So we're going to say that our hypotenuse equals 1, which means we have x radical 2 is equal to 1. And now once we have that, we can actually solve for x. And solving for x is going to be what helps us when we get to our unit circle. So let's see how long, if the hypotenuse has a length of 1, how long is each of these sides going to be? So we can divide by square root of 2, or radical 2 as we call it. And we find out, we're going to draw an arrow and go over here. We're going to find out that x equals 1 over radical 2. And as a remnant of the old way of doing math before we had calculators, we like to rationalize our denominators. So we don't like to have radicals in the denominator. They make things harder when you're using tables instead of calculators. So all we do is we multiply by the square root of 2 on the top and by the square root of 2 on the bottom. And really, essentially, we're just multiplying by 1. And we get x equals radical 2 over 2. In a 45, 45, 90 triangle, if the hypotenuse equals 1, each side has a length of radical 2 over 2. The next triangle we're going to look at is a 30, 60, 90 triangle. Now, this is another special triangle with special side relationships. In the triangle that we have here, we have our right angle at C, again, like last time. We have angle A off to the side, and that's the angle that we're going to be interested in for the unit circle, and angle B up here. So in this case, we have our 30-degree angle at angle A, our 60-degree at B, and our 90-degree at C. In a minute, we're also going to look at this flipped in a different direction so that the 60-degree angle is at A. But for now, let's work it out as is. And in this triangle, we have the shorter leg equal to x, the hypotenuse equal to 2x, and the longer leg is going to be x radical 3. And these values of x can be anything. It just means that the hypotenuse is always twice as long as the shorter leg, and the longer leg is radical 3 times as long as the shorter leg. These are just relationships between the sides if you have a 30, 60, 90 triangle. So let's go ahead and set our hypotenuse equal to 2x. And remember that we want that to be equal to 1 in our unit circle. So if 2x is equal to 1, then we can quickly see that x is 1/2. So this shorter leg right here is going to be 1/2. And if we go ahead and plug in our 1/2 value, substitute for x right here, we'll get x radical 3 equals 1/2 radical 3. And we end up with x radical 3 equals radical 3 over 2. So if our hypotenuse is equal to 1, then our shorter side, our vertical side in this case, equals 1/2, and our longer side, which is the horizontal in this case, is equal to radical 3 over 2. And finally, we're just going to look at the same triangle, the 30, 60, 90 triangle, but this time oriented a little bit differently. The math is going to be the same for this. We find that 2x, the hypotenuse, we're going to set equal to 1 because that's what we want for our unit circle. And then doing the algebra, we find that x equals 1/2 and x rad 3 equals radical 3 over 2. The only difference in this case is that now our x is the horizontal, so our horizontal is 1/2, and our x radical 3 is the vertical, so the vertical is radical 3 over 2. Let's look at both triangles side by side, and we'll see when we put them side by side that the values are the same. But in this one, the x is on the vertical and it equals 1/2. And in this one, the x is on the horizontal and it equals 1/2. And vice versa for the x radical 3's. That's important to keep in mind when we're looking at our unit circle with sines and cosines. And it will help you keep track of which angle we're thinking of at any given time, because you'll always be able to come back to these triangles.